Hi there, this is Capacitance, Lesson 3, Parallel Plates. So if a material contains polar molecules, they will generally be in random orientations. So that's this one, the first one. When no electric field is applied. An applied electric field, so if we put an electric field across this, will polarize the material by orientating the dipole moments of polar molecules in the same direction. So they'll line up. Now these types of materials, these dielectrics, are the materials that we put in between capacitor plates. So you can have capacitors that use air as an insulator to set up an electric field, but you can put these materials in there, and these will make the capacitors, of higher value, so they can store more charge per unit volt. And that's what you need to know essentially. You could be asked about this in an exam, and you just need to say, if you set up a potential across it, a potential difference or a voltage, that the polar molecules would line up in the same direction. So as you can see, the difference between the first image and the second one. Top one's all random, and the second one, they're all arranged all in the same direction. As you can see, positives at the top towards the negative, and negatives at the bottom towards the positive. So let's move on. So the capacitance of a charged parallel plate is increased by the introduction of a dielectric material. The capacitance is inversely proportional to the electric field between the plates, and the presence of the dielectric reduces the effective electric field, thus increasing the capacitance. So here's some examples. So we've got the material and the dielectric constant. So we've got air, which is a dielectric constant of 1, which is similar to a vacuum. Bakelite 4.9, mylar 3.2, nylon 3.4, paper 3.7, and then some other materials that are used in capacitors. And as you can see, some of them, this strontium at the bottom, increases capacitance by a factor of 233. If you want to pause and make some notes on the writing at the top, that's fine. And then just unpause when you're ready to move on. So, parallel plate capacitor equation. So the capacitance is equal to, now we've got epsilon naught, which is the constant, epsilon r, if applicable. A lot of these questions you won't need to use the epsilon r. It depends if there's a dielectric material present in the question. Multiply by cross-sectional area, divided by the distance between the plates. So capacitance is measured in farads. Epsilon naught, the number is 8.85 times 10 to the minus 12, and its unit is farads per meter. Now epsilon naught is the permittivity of free space, and it is an ideal physical constant that represents the absolute dielectric permittivity of a vacuum. So it sort of quantifies the ability of a vacuum to allow an electric field to be present. So let's just write this out. So permittivity of free space. Epsilon r is just a number, the table which I showed you previously. So epsilon r value could just be 2.4 or 3.7. Area is obviously measured in meters squared, and distance between the plates is measured in meters. So let's move on. Let's utilize this equation. So we're going to calculate the capacitance. That should be of, not PF. I apologise. Calculate the capacitance of a parallel plate air capacitor consisting of metal plates 1 times 10 to the minus 4 meters apart, and a surface area of 5 times 10 to the minus 3 square meters. Assume the permittivity of air is the same as the permittivity of free space. If you want to pause and have a go, and then I'll take you through the answer. So we simply need to use the equation. So capacitance is equal to epsilon naught A over D. Then just put our numbers in. So epsilon naught is 8.85 times 10 to the minus 12. Multiplied by the cross-sectional area, 5 times 10 to the minus 3. Divided by the distance between the plates, 1 times 10 to the minus 4. If you put that in your calculator, that'll give you a capacitance of 4.4 times 10 to the minus 10 farads. Let's try the next one. So this time, calculate the capacitance of a parallel plate air capacitor consisting of metal plates 1.2 times 10 to the 4 meters apart and a surface area of 400 millimeters squared. Assume the permittivity of air is the same as the permittivity of free space. If you want to pause and have a go. So on this one, it's exactly the same equation. Only this time we need to convert the 400 millimeters squared. You should be okay at this point of your studies, but just as a reminder, so 400 millimeters squared, so we pretend it's millimeters and just do times 10 to the minus 3. And then it's squared, so we times by 10 to the minus 3. Yet again, multiplied by 1 times 10 to the minus 3, which gives us cross-sectional area of 400. And then we add the indices times 10 to the minus 6 square meters. So that's what we're going to use. So now its capacitance is epsilon naught A over D. Then let's put the numbers in. So we've got 8.85 times 10 to the minus 12, multiplied by the area, 400 times 10 to the minus 6 square meters, divided by the distance, 1.2 times 10 to the minus 4. And if we calculate that, that gives us a capacitance of 2.95 times 10 to the minus 11 farads. Let's do the next one. Let's pause and have a go at this one. So this one, calculate the capacitance of a parallel plate air capacitor consisting of metal plates 20 millimeters apart and a surface area of 500 millimeters squared. Assume the permittivity of air is the same as the permittivity of free space. And this time we've got a dielectric constant of nylon used as an insulator. It's been introduced with a relative permittivity of 3.4. So if you want to have a go at that, just do it. And then I'll take you through the answers. So capacitance is equal to, this time, epsilon naught, epsilon r, because we've got the dielectric constant, multiplied by area divided by distance. So then let's just put our numbers in. So epsilon naught is 8.85 times 10 to the power minus 12, multiplied by epsilon r, the dielectric constant, which is 3.4, multiplied by the area, so that's 500 times 10 to the minus 6, divided by the distance between the plates, which is 20 times 10 to the minus 3 meters. So that gives a capacitance of 7.5 times 10 to the minus 13 farads. Okay, a bit more information now. Remember to pause at any time. So be careful. You get these questions quite a lot in exams, so we've got to be careful. So if you increase the distance between capacitor plates after you isolate a power supply, so that's normally a capacitor that's been charged, and then after it's been charged, they remove the voltage across it, and then increase the distance between the capacitor plates and ask what happens. So if the power supply is disconnected, then it is the charge on the plates that remains constant, and the potential difference between them increases as the plates are separated. The electric field intensity would remain constant in this case. It's important. I would probably write that down, put a big box around it, read through it, make sure I understand it, because it's an important concept. So let's do some questions now. So in this one, the separation of the plates of an isolated charged parallel plate capacitor is increased. What else also increases? So if you've took your notes, you would know that the other thing that increases is indeed the voltage. Okay, let's move on to the next one. So let's pause and have a go at this. A parallel plate capacitor that uses air as an insulator is charged. The electric field present has a strength E. The capacitor is disconnected from the power supply and the separation between the plates is doubled. What happens to the electric field strength in terms of E? So it should be pretty straightforward. The capacitor is disconnected. So if you've written the notes down earlier, once it's disconnected and the separation of plates increases, the voltage would increase. But what would happen to the electric field strength? Well, the electric field strength will just be the same, it remains constant. So in terms of E, the electric field strength would simply be E, be the same. Hopefully you got that one. Let's move on to the next one. So if you want to pause, have a go at this question. A capacitor consists of two parallel square plates of side L separated by distance D. The capacitance of the arrangement is C. What is the capacitance of a capacitor with square plates of side 2L separated by a distance 0.5 D in terms of C? So on this one, we just need to look at capacitance. So capacitance is epsilon naught A over D. So we've got side L, and this time we've got side 2L. So area is obviously the length times the length, so we've got 2L times 2L. And 2L times 2L is 4L squared. And the distance is 0.5 D. So we just need to write out this equation. Capacitance is epsilon naught. A is, we've got 4 times the area, divided by 0.5 D. So what's changed compared to the original, this one's the original, the first one, what's changed is we've got a 4 divided by 0.5. 4 divided by 0.5 gives us a capacitance in terms of C, 8 lots of C, compared to the original. Hopefully you got that one. Let's do one more. Parallel plate capacitor has square plates of length L separated by distance D and is filled with a dielectric. A second capacitor has square plates of length 2L separated by a distance 2D and uses air as its dielectric. Both capacitors have the same capacitance. What is the relative permittivity of the dielectric in the first capacitor? If you want to pause and have a go at that one. So in this instance, both of the capacitances are the same. So I can say that the capacitor 1 is equal to the second capacitance. So the first one, capacitance, is epsilon naught, epsilon R, A over D. Well, we could say, because we've got length, we could say L squared. Let's go back a bit. Distance D equals, we've got epsilon naught. We haven't got the dielectric because this is the second plate. There is no dielectric. So there's no epsilon R. Then we've got distance 2L, length 2L. So that would be 4L squared. Divided by, then we've got 2D. So 2D. So what we can do is cancel out the L's. So the L's go. We can cancel out the epsilon naughts. And we can cancel out the D on each side. So these aren't balanced anymore. On the right hand side we've got 4 over 2, which is this is 2 times greater. Which means that the left-hand side would also have to be, we have to multiply it by 2. And the way to do that is if the dielectric constant had a value that was equal to 2. Hopefully that's okay. Thanks for watching, and I'll see you soon.